Hi, Year 13. In today's lesson, I'm going to show you a new technique for integration called integration by parts, as you can see on the screen. Before that, though, I've got a quick recap question on integration by substitution. So if you want to have a quick go at this, you're welcome to by pausing the video, and then I'm going to come back to it and go through it, and then we're going to move on with the new part for today. So pause the video and have a go. Okay, cool. Let's have a look at this. So we're integrating x cubed over the cube root of x to the 4 plus 1 dx. I've told you what substitution to use. That's u equals x to the 4 plus 1. But if we take a look at what we're integrating, firstly, it seems pretty obvious that that's going to be our substitution because that's composed inside this cube root here. So it's going to make that awkward if I leave it as it is. And also, what's nice about this integral is that I've got what looks like the derivative of u sitting on the top here. So this x cubed is related to the x to the 4. So when I differentiate my u function, it's going to be quite nice because my x cubed is going to appear as well. So let's see what we can do with it. So here's my u. I'm going to differentiate first and figure out dx. That's going to be 4x cubed. Now, as I said before, this x cubed is already sitting here, and so I'm going to keep it on this hand side and just times by dx first. Oops. And then because I've got x cubed and dx matched up already, I'm just going to divide by 4. There we go. So then when I rewrite my integral in a second, this part in pink is going to be written as this part there, because that's x cubed dx as well. Right, let's rewrite our integral then. We'll do everything in terms of u. So I'm now integrating something over the cube root of u, which is my x to the 4 plus 1. And then x cubed dx, I've said before, that's a quarter du. Now the quarter is a constant factor. I'm going to bring that out to the front, and that's a 3. And then the rest is just du. So it's 1 over the cube root of u du. Okay, this is much easier to integrate now, but before I can do that, I need to write that as a power. So a quarter at the front, and then this is going to be integrating u to the minus 1/3. Now I can integrate that using the power rule. So that gives me a quarter u to the 2/3 by adding 1, and then you divide by 2/3 plus c, and then dividing by 2/3 multiplies this quarter by 3 over 2, and that's going to turn it into 3/8. And then we're nearly done. All we need to do now is reverse our substitution back to things in terms of x, and u is x to the 4 plus 1. So here's my final answer. And we're done. Okay, hopefully you got that right. That's just a bit of a recap from last time. So now we're ready to move on with integration by parts. Okay, so what is this? What does this do? So effectively, integration by parts is just reverse product rule by another name. So as you can imagine, it's a rule for integrating products. So if we think about how the product rule works in terms of differentiation, we can hopefully, in some sense, reverse this just to enable us to integrate products instead. So starting off then, so if I want to differentiate a product, and I'm going to write my product of functions as u times v to use some simple notation. Okay, I could be using f and g, but that works just as well. So u and v are functions of x. Okay, now we know from the product rule that differentiating this product gives us this stuff. It gives us the derivative of u times v, and then plus u times the derivative of v. So I'm going to write that this way. I'm going to write it as v du by dx. That's 1/2 of the product rule, plus u dv by dx. Okay, so that's the normal product rule that we know and love. I'm now going to integrate both sides of this to write things in terms of integrals. So integrate this side dx, and also this side. And think about what that gives us now. So on the left side of the equal sign, I've got a derivative of uv. If I integrate that, then these are inverse operations which are going to cancel out. So integrating this is going to get me straight back to uv again. Then on the right side, these are separate functions that I need to integrate separately. So this is integrate v du by dx, and then that's dx, plus the integral of u dv by dx, again times dx. Right, that's integrated both sides. What we can now do is cancel out the dx's that appear here and in the denominator, and that makes the integral look a bit tidier. So I'm going to cancel these and cancel these. And then finally, I'm going to subtract one of these integrated terms onto the other side. So what I'm effectively going to do is I'm going to solve it for this term over here. Okay, so with a bit of rearranging, we've got this, and this is our integration by parts formula. So the integral of u dv equals uv minus this term in the middle, which is the integral of v du. Okay, so I'm going to box this around. This is my integration by parts formula, which I'm going to refer to as IBP. Okay, and this is quite useful. So it works like this. So if you're integrating a product, then we label up the product in terms of a function u and then a differentiated function v. So this over here, if you remember, is 1/2 of the product rule when we differentiated this stuff. And the idea is that you use these terms, and the integral that appears over here is the other half of the product rule. Maybe I should write that out. So this is half of a product rule, which we're going to swap over and instead integrate this part. And hopefully, if we've done things correctly, this part over here is going to be a simpler integration. Okay. And you also notice that to swap over from this integral here to this integral here, the dv portion has been integrated back to v, and the u portion has been differentiated back to du. So there's a swapping over in terms of integrating one of these things and differentiating the other. Okay, so that there has integrated, and these green bits have been differentiated. Okay. Now I think best thing to do is probably see an example so you can see how this all works, but it's worth you writing down that formula so that you can use it, and I believe it's also in the formula book as well. Right, first example. Let's integrate x cos x dx. Right, so clearly this is a product, which implies that integration by parts is the best way to go. And when you set up your integration by parts, you get to pick which of the parts of the product are going to be called u and which is going to be called dv. I think it's probably best to write the formula down first of all. So integrate u dv equals uv minus integrate v du. Okay, so we're going to choose which one we're going to integrate and differentiate. Now, from what I know about differentiation, a polynomial function like x to a power of something, is going to simplify itself when I differentiate it. And on the other hand, it's going to make itself more complicated if I integrate it. So it looks as if the x is the thing that I want to be differentiating, not integrating, because I want to make things simpler for myself. Cos x, on the other hand, it doesn't particularly matter. If I differentiate it, I'm going to get minus sine, which is no more simpler or more complicated. And if I integrate it, I'm going to get positive sine x. So again, that's not going to matter if I integrate it or differentiate it. So I'm going to choose to let u equal x, and I'm going to let dv equal cos x. Okay, so I've assigned these bits of the product with these parts of the integral in my formula. Right, now I've done that, I'm going to differentiate this one. And I'm going to integrate this one. And that's going to give me the other parts of my formula that I can use on the right-hand side. So du by dx is just 1. Okay, and it's also standard at this point to solve for du. It's not particularly important that you do this, but it does make sense when you come to do this bit. So du equals dx over there, just by times my dx. Right, integrating dv gets us back to v, and integrating cos x with respect to x gives us sin x. And then we're done. We don't need a plus c for this part. I just need to know an antiderivative without needing plus c for this to work. So now I've got these four in this this diagram here. I need to stick everything into this right-hand side. So the integral of x cos x dx equals, well, firstly it's u times v, and that's going to be the product of this diagonal over here, because here's u and v times together. So the first part of this is going to be x times sin x. Then I've got this minus here, and then it's the integral of the bottom row of this times together as well. Okay, so the integral of sin x times 1. Okay, and then du appears in the formula, but we can write that as dx, so I'm going to do it like that. And that's the reason for doing that step. Okay, as long as you write dx in that part, it doesn't particularly matter. So you're integrating x's. Right, so have you noticed then that our choice of x and dv has resulted in a much simpler integration over here? Okay, there's no x that's getting in the way, it's differentiated and disappeared to 1, so this is going to be easier. So now this is just x sin x. I'm just going to tidy up the 1 and write it as the integral of sin x. If there are multiple minus signs, it's worth bringing them out to the front, which we'll see in a moment. And then sin x integrates to minus cos x with a plus c, and then the double negative is going to cancel out. And that's done. Okay, so that's your first example of integration by parts. And as we go through, you'll get the idea as to which we choose for our u and our dv. And there's generally rules of thumb as to how this works. Okay, so for now, I'm going to write down the fact that we chose our x to the power to be our u. So this simplifies when I differentiate it, so it's best to use that as your u. There we go. Okay, next example. So secondly, I want to integrate x squared ln of x dx. Okay, so again, we're going to write the formula down. Integrate u dv equals uv minus integrate v du. Okay, so again, we get to pick which of these is the one that we want to integrate and which is the one that we want to differentiate. However, because there's an ln of x appearing in our integrand, we don't actually have a standard way of integrating ln of x. So unfortunately, in this case, we are forced to choose this one as the one that we can differentiate, because I do know the derivative of ln of x, but not its integral. So for this case, we're going to choose u to be our ln of x and our dv to be x squared. Okay, so ln of x, I'm going to write it can't integrate. So we're forced to put it as our u this time. And that's always going to be the case with an ln of x. Okay, now we can continue. So I want to differentiate this one. Du by dx. ln of x differentiates to 1 over x, which means that du is 1 over x dx. Okay, differentiate this side. Okay, we integrate this side, which unfortunately makes it more complicated, but it's okay because when we do the next bit, it's going to all make sense. So v is x cubed over 3. And now we can use the formula. So firstly, uv is that times that. So the integral of x squared ln of x dx is x cubed over 3 times ln of x minus the integral, and now we're doing this bit, v du is x cubed over 3 times 1 over x dx. Okay, and again, make sure you've got a dx there, not a du, because we've got it in terms of dx. Now, the way that this is arrived at is that we can simplify this quite a lot, because the x cubed cancels with x. So I've now got x cubed over 3 ln of x minus the integral of just x squared over 3 dx, which becomes x cubed over 3 ln of x minus, and then x cubed, and then dividing by 3 gives us over 9 plus c, and then we're done. Okay, so then to reiterate, although the previous example I said to differentiate any x to the n's, because of the ln that's appeared, we've forced us to have to differentiate that term there. Okay, let's see some more examples. You're welcome to skip through these and look through them in your own time, but I'm going to do as many as I can to cover as many bases as possible. Right, next we've got integral of x squared e to the x dx. Okay. Right, so according to my advice, we've got a polynomial term here, and that's going to simplify when I differentiate it. And I've also got an exponential term that's going to stay exactly the same when I differentiate it or integrate it. So in this case, it makes sense to be differentiating x squared and integrating e to the x, because that's going to stay as e to the x no matter what I do. So I'm going to let u equal x squared, and then dv equals e to the x. And again, I'm going to write down the formula. That's not it though. All right, integral of u dv is uv minus integrate v du. Right, x squared differentiates to 2x. So I'm going to write du is 2x times dx. That saves me a step. And then the integral of e to the x is still e to the x. Integrate. Okay, use the formula now. uv is just x squared e to the x again. Then I'm going to subtract the integral of e to the x times 2x dx. Okay, right, oh dear. Okay, so we're now in a position where our integral on this right-hand side is indeed simpler, but we've still got an x at the front that still is forcing a product here. So unfortunately, we've got to use integration by parts twice. Okay, we've got to do it a second time. So the first thing I'm going to do is I'm going to firstly, actually no, I'm not going to factor out the 2, I'm going to keep it as it is. So I'm going to just write it as this. Minus, okay, so now I'm going to do this. So I'm going to put some big brackets in. And then over here, I'm going to write down what I do if I'm going to integrate by parts again. Now, with a bit of abusive notation, I'm going to use u's and v's again, as long as I realise that I'm doing a separate integration by parts. So I'm going to let u be 2x this time, and I'm going to let dv equal e to the x. Okay, if you want to use different letters to u and v, you can, but I'm just going to do a bit of abusive notation there. Right, du equals 2dx. V is still e to the x. So for this integral here, I'm using this integration by parts, which is going to give us 2x times e to the x minus the integral of v du, which is 2 e to the x dx. Okay, so now I've got this integral nested inside this bracket, but it's a much simpler one without anything in terms of x at the front, so I can straight up integrate this function here. You just now got to be careful about expanding this bracket out. So let's do that first. Let's expand the bracket. So x squared e to the x minus 2x e to the x, and then double negative here, plus the integral of 2 e to the x dx. Now the only thing left to do is integrate this last part. and then e to the x goes straight to itself with a 2 at the front. And that's plus c. Okay, and that's done. So just bear in mind then, so sometimes x to the n requires multiple integration by parts to make sure that all the x's disappear, leaving just a constant at the front like we did here. Excuse me. Okay, I'm going to do a few more examples. Right, integrate x squared sine x this time. Okay, so we've got another x to the power of next to sine x. And again, thinking about what happens when we differentiate and integrate these, I think the best course of action is to differentiate x squared and integrate sine x, because sine x just goes to either cos or minus cos. So it's up to us what we choose for that, but then that will become simpler if we differentiate. Here's the formula again. uv minus integrate v du. I'm going to let u equal x squared. I'm going to let dv be sine x. du equals 2x dx. V is minus cos of x. So now I can use the formula. So my integral, if I call it I, which is normally what we tend to do for an integral, I'm going to not write it out again. So my integral is x squared times minus cos of x is this, minus the integral of minus cos x times 2x dx. Okay, and then again, we've got another product rule here that requires a second integration by parts. But before that, I'm going to tidy this up together. So this becomes this, plus the integral of 2x cos x dx. Okay, right, let's write out our second product rule. So I'm going to make this have u equal 2x, dv equals cos x, which means that du is another 2 dx, and v is going to be positive sine x. Now we can carry on. So x squared cos x plus, okay, so now in this bracket I'm going to put the new product rule. This is going to be 2x sine x minus the integral of 2 sine x dx. Right, brilliant. And now, as we did in the last one, this has become a much simpler integral than what we had at the start. There's no x's, so we can just straight up integrate. So what we've got now, minus x squared cos x plus 2x sine x, and then the integral of sine x is minus cos x with the 2 at the front. And then double negative makes plus. You've got to be really careful about these minus signs here, and it helps to write out lots of steps so you don't lose any of them. Sine x plus 2 cos x plus c. There we go. Okay, that one's done. Right, two more that I want to have a look at. Again, you're welcome to skip through the video as you see fit. But there's an important thing to be learning in each one of these that I've done. Okay, so now I want to do just ln of x dx. And again, I'm going to write the formula down. Okay, so this is just ln of x on its own. So you might be wondering about why this has anything to do with the integration by parts, which involves products. But we said in a previous example that ln of x doesn't really have a straightforward way of integrating it. Okay, we don't particularly like integrating inverse functions in particular. Okay, ln of x is an inverse function of e to the x. So what we do for this one is there's a little trick to do. So instead of integrating ln of x, is that we use integration by parts to differentiate it instead, and then get the integral in that manner. So I'm still going to do integration by parts, but what I'm going to do is I'm going to let u equal ln of x and then I'm going to let my dv be equal to 1. Because what I've really got here is I've got ln of x times 1. And if you think about it that way, that's a good way of using integration by parts with a little trick. So here's my setup for this one. I'm going to differentiate this one, integrate the 1 to get me to x. Now I'm going to use the integration by parts formula. So again, let's call this I. And that's uv ln of x times x minus the integral of x times 1 over x. I'll write it this way, sorry. Okay, and that's good because x times 1 over x makes 1. Okay, or just dx if you like. And the integral of 1 is just x. Okay, so here we have the antiderivative of ln of x. Okay, and we kind of did it without really integrating ln of x at all. We differentiated it. Okay, but then as a check, we can check that this differentiates back to ln of x. And it should make what we've got. If I use the product rule on this, I'm going to get x times the derivative of ln of x, which is 1 over x. And then the second half of this part is going to be the derivative of x, which is 1, times ln of x on its own. And then x differentiates to 1. And as you can see, that's a 1 that cancels out with this minus 1. And you're left with just ln of x. So we're good. All right, so that's quite an important tool there. So any inverse function can be done by using this technique here of setting dv equal to 1. And if you want an extra bit of practice on that, you can use the exact same method to integrate inverse trig functions. So I suggest, if you want to, you can try the integral of arctangent of x using the same method. Okay, so you're welcome to pause that and have a go, or do it after you've finished watching the video and see what you can get with that. Okay, final example. This is quite a complicated one, but it's one that's worth you seeing because I've seen it in an exam as well, so it's worth you having a look at it. So we're integrating e to the x sine x, which is kind of a strange one. Okay, and this came up in an exam a few years ago, and it confused a lot of students. So it's worth you seeing this one. It's quite an important example of a special case. All right. So I'm going to firstly write down the formula as before. Now, let's think about what happens when we integrate and differentiate these. So e to the x both integrates and differentiates to itself, so we've got some flexibility of choice there. And sine of x, similarly, will either go to cos or minus cos, depending on whether you integrate or differentiate. So it's up to us, really, which one we choose for our u and which one we choose for our dv. But I'm going to set my u to be e to the x and my dv to be sine x. It works the other way around, but that's fine. Okay, differentiating this side gives me du equals e to the x dx. And integrating sine x gives me minus cos of x. Okay. Now, before I start, it's important that for this example in particular, I'm calling this integral I, for reasons that I'm going to explain when we get to it. So, my integral I is now uv, which is minus cos x times e to the x, minus the integral of minus cos x times e to the x, which gives me a second minus sign in here. Okay, that's step one. Now I'm going to tidy up this double negative here and make it positive. So we're adding the integral of e to the x cos x. But what we've got now is we've got another integration by parts which looks similar to this one but isn't quite the same. So let's see what we can do with this other integration by parts. It's looking a little bit futile now because we're in no better position than what we were before. But let's see what happens after the next step. So for this part, I'm going to let u be e to the x again, and dv be this time cos x. Again, a bit of abusive notation because I've already used those letters, but we're going to separate them and keep them separate. Okay, du is again e to the x dx, and this time v is the integral of cos x, which is sin x. Okay, second application of IBP gives us this, minus e to the x cos x, plus, and then we've got this, e to the x times sin x, minus the integral of e to the x times sin x again. Okay, right, let's take a moment to consider what we've got now. So now I've got a term over here that's worked out, another term here, and then also this term on the end here, you'll notice is the exact same as the I that I'm trying to work out at the beginning anyway. So we've now got to recognise that this part here is equal to I. Okay, so now what I've done is, because I've written my integral as this capital letter I can write an equation in I. Because I've now got I equals minus e to the x cos x plus e to the x sin x minus I. And what I can do with this is I can now solve this for I. So by adding I to both sides, that gives me 2 lots of I equals minus e to the x cos x plus e to the x sin x. I'm not going to add c just yet. But now I can halve everything and solve for single I. So I equals minus a half e to the x cos x plus a half e to the x sin x. Okay, now I'm going to add my c because it saves me the step of rewriting c over 2 as just another constant c. So there we go. Right, so that's quite a strange one. You end up integrating by parts twice, and then you get the same integral back again, but unfortunately it's got to be a subtraction for this to work. If this was addition, these would cancel out and we wouldn't be left with anything else. So that's quite a strange one there that you've got to be aware of. Okay, I think that's all the examples that I'm going to have a look at. So hopefully that's enough for you to get going with some of these. If you need any help, then please let me know. Thanks very much, Year 13.